This is an introduction on how to integrate extensions to libCL with OpenCL Studio. Now, even though libCL is a completely standalone open source parallel algorithm library, you can download it from Google Code Hosting, it's very tightly integrated with OpenCL Studio. As a matter of fact, most of the demo applications that come with a download rely on the algorithms within libCL. Now you can access the constructs within libCL via the pop-up menu here in the OpenCL Subtree. And if you go down to libCL, you can see different categories, and under each category there's a number of different algorithms. So I will just choose here a recursive Gaussian. And now here in the tree view you have a recursive Gaussian program object. And if you click on the code tab, you can see the source code. Now if you have a look at the bottom here at the tab, you can see there's actually a path here to a text file within the libCL subdirectory. So this is a little bit different than the normal OpenCL program node, which stores the kernel code within the project file. Here you're actually referencing a text file within the libCL subdirectory. So we can now use the recursive Gaussian like any other program object. We can drag and drop it into a script processor, implement the event handlers, and then call the various functions that this program publishes. And I will show you later how to actually implement these functions and how to make them available to the scripting API. Another place where you can find libCL is here under the Help tab. Under the libCL subtab over here, you can see a list of all the algorithms that are currently available. And then when you select an algorithm, you can over here see a documentation of the API. So as you can see, OpenCL Studio already comes with its own version of libCL. You can find it under the workspace directory, including all the source codes and makefiles. And I will now show you how to integrate your own classes into this framework so that they show up within the editor in the manner that I just showed you. So the first thing we'll do is we'll create a new workspace, which will actually make a copy of libCL as well as all the other plugins into its own directory. So you can manage different versions of libCL using different workspaces in OpenCL Studio. And you create a new workspace by going up here to File, New, Workspace. So after you've created your workspace, we now have to switch over to the File Manager and actually open that workspace directory. And once you've done so, you will see a directory that looks something like this. So at this point, we're only interested in the bindings directory. It contains 4 other directories, and at the bottom we have plugins. Now this plugins directory contains all of the Lua extension modules, which is another way of extending the scripting API in OpenCL Studio. But it's its own topic and it has its own tutorial video dedicated to it. libCL is integrated somewhat differently. So above the plugins there is the liblua directory, and this one contains the header files and DLL for the Lua scripting engine. Now this is basically necessary to develop any extension to the Lua language, and both the plugins as well as the libCL bindings, they both need to refer to these header files. So the next directory is the actual libCL. And when I open it, you will see a directory structure and files, which is exactly the same as if you would download libCL from Google Code Hosting. Right here, there is a number of base classes, and then up here there is different directories, each of which contains various algorithms. And an algorithm in libCL basically consists of a header file, a CPP file, and a .cl file that contains the OpenCL kernel code. So the last thing in the bindings directory is libbind, and this library basically binds the classes in libCL to OpenCL Studio. And this includes registering them with the editor as well as defining the Lua scripting interface. So this directory also contains a DLL called libbind, which is opened by the editor every time it starts, and basically gives it the information about which algorithms are currently available in libCL. And this DLL is built via a single Microsoft Visual Studio solution called libbind.sln, and when I open that, this is what it looks like. So within this solution, there are now two projects, one called Lipbind and the other one's called libCL. And libCL looks very similar to the directory structure we've seen earlier. Here are the base classes, and then up here you have different categories, and with each category there is a .cl, .cpp, and .h file per algorithm. And in Lipbind, now it looks also very similar, and for each category there is now a single header file that contains the bindings. So let's now go through a scenario of adding our own algorithm to libCL. We'll actually not create a new class, but rather we'll use an existing one to illustrate all the steps that are necessary. So as an example, we will use the recursive Gaussian, and this is here under the filter category, and here are our three files: recursive Gaussian CLL, CPP, and .h. And we'll start by having a look at the .h file. So in here now we have our new class declaration, OCL recursive Gaussian. In libCL, every new algorithm derives from the OCL program base class. And then below there we have a few function declarations and members, including a kernel object. So let's have a look at the CPP file. Right here is the constructor. One thing to note here is this first line, and it adds the OpenCL kernel code now to this program. Below here there is a compile function, and then below there are two functions that are specific to this algorithm. The setSigma function, if you see here, it sets several kernel arguments, and the compute function is down here. It actually executes the kernels. Other than that, there is still the .cl file, and this one basically contains the OpenCL kernel code for the recursive Gaussian. So if you were to write your own class, you could use one of the existing ones as a guide. You'll basically create three files and place them in any one of these subdirectories, or you can create your own subdirectory. So once we have added our class to libCL, we go up to Lipbind and add the corresponding header file. Now again, you can use an existing one as a guide, and in the case of recursive Gaussian, here's what it looks like. So the first thing in here is a class declaration for bind recursive Gaussian. It derives from a template class, which we'll basically not concern ourselves with. Then there is the constructor, and for the constructor there is a function called init. And this is the first time we'll actually see the Lua scripting engine. And within the init function we call the base functionality, and then here we declare two methods, compute and setSigma. Now these will be methods that we can later on call via the scripting interface in OpenCL Studio. So below here we're now supplying the implementation of these functions, which are called directly from the Lua interpreter, and the only parameter to them is the Lua state. And within here there is now a number of calls to retrieve the parameters to the compute function as it's being called from the scripting interpreter, and you pop these parameters from the Lua stack. Now if you'd like to learn more about how Lua works, there's lots of information available on the web about the Lua scripting engine. Now once we've retrieved all the parameters, down here we're actually calling the compute function of our corresponding class in libCL. And then the similar thing is happening down here for the setSigma function. So now that we created our new libCL class, we have created our binding class. The only thing left to do is now to register our new algorithm with the editor. And we do that in libbind.cpp. Now this is actually a somewhat a larger file. It contains all the DLL functions of Lipbind, but we're not interested in any of these. All we're interested in is a little section right here where we include different algorithms, and we have to own include right here. And then we go down a little bit further, and there is a registry table that contains all the classes, and we have to add another entry with our bind recursive Gaussian class right here, and that's it. All that's left is to compile. So I now build the solution. It will first compile libCL, and then it will compile libbind to create this DLL in our binding subdirectory right here. So the next time we start OpenCL Studio, it'll load this DLL and we'll be able to find our algorithm right here under the libCL pop-up menu, recursive Gaussian. And we can then, once we have added it and selected it, we can now actually see our kernel code, and it'll show us the path down here to the .cl file we have created earlier. You can now, within OpenCL Studio, change the kernel code and actually save the .cl file within a libCL subdirectory. So it's almost easier if you are developing a new algorithm for libCL to leave the kernel code empty and actually implement it within the framework of the editor so that you can easily navigate to compiler errors and maybe write little test programs. One thing left to show you is how to integrate your own help into the help system in OpenCL Studio. So if you click at recursive Gaussian, and for each function there is a description here. This will also pop up in the code completion window over under the scripting tab. And the way to add your own descriptions for your own algorithms and functions is via the libbind.xml file. So this file also resides in the libbind directory. It's loaded at the same time as libbind.dll. And in here you can now use this XML syntax to define your own function documentation. I believe the XML is quite self-explanatory, and this file contains ample of examples of how to do that. So this basically wraps up the tutorial on libCL. I believe that the source code for Lipbind and libCL that comes with the distribution of OpenCL Studio provides ample of examples on how to implement your own extensions. At this point, I'd also like to point you to another tutorial on how to develop Lua extension modules, which is another way of extending the scripting interface for OpenCL Studio.